Good evening, welcome, namaskar, sat sri akal, hola, bonjour. Welcome all my lovely warriors. Welcome to the Zero to Superhero series for all the 2022 aspirants who want to crack your JEE or NEET examination. And this is We Enlite, the English medium channel. And today we are going to talk about electricity, magnetism's final part, which is, the magnetism effects as well as the sources. In tomorrow's class, we are going to discuss EMI and AC. So all about magnetic effects and sources for all the 2022 aspirants, JEE and NEET. With me, Shreyas, your physics master teacher at Vedantu. Thank you, Ankit, for all the colorful welcome. And guys, you know what to do. Go ahead, smash the like button down there. And also, if you're new to the channel, hit the subscribe button if you want all the content in English medium and you don't want to miss out on all the awesome classes that we conduct here. You need to go ahead, hit the like button if you have already hit the subscribe button so that you can shower your love and your support. And I can't stress on the fact more that, it means a lot for all of us. There is a Telegram link also where you will get the PDF and also the updates on the upcoming classes. Make sure you are already a part of it. Welcome my warriors. Let's see who and all are present. Welcome guys. Motivation session, Ankit, you heard it. Saturday 7 o'clock. Saturday 7 o'clock motivation session. Saturday 5 o'clock, you're going to have 5 or 6 o'clock, a casual talk session and interaction for all the students with me. Smashed it yesterday. Thank you so much, Ankit. Hi, PL. Some of you already smashed the like button even before the class starts, and it means a lot. It shows your love. Hi, Daljan. Hi, Suhani. Hello, Sujata. Hi, Abhimanyu. Hi, God is love. Thank you so much, Bacha. Hello. So let's begin with the class. And do not forget that if you have anything to say, even after the class, you can always leave your comments after the session is over. All right. So all the links which are there are over here in the description box. You can click more. And there is a special surprise for all of you. Most of you also wanted some assignments. So I'm going to give you some homework questions. The main assignments are obviously there in our crash course. The link is there over here, both for JEE and NEET. They are separate assignments based on the separate pattern for JEE and NEET. And this crash course is in complete English medium. So it is definitely going to benefit you. It also has test series. Right now over here, you can also see the link of the homework. You just click on it. Right now I'm the admin, so it will show like this. But for you guys, you'll be able to play and participate in this particular week quiz. Okay, so make sure you solve the questions in the week quiz after the session is over. So let's begin, guys. And the expected dates should be anywhere in June or June end, Bacha. Good morning, Jamesburg. Looks like you are from the other side of the world. Venkat, I am going to conduct a motivation session on Saturday, 7 o'clock, guys. Keep that in mind. Good evening, Rihan. How to get 100 plus in NEET? Whether we should study all lessons. 100 plus, you don't need to study all the lessons. There are some topics which you can skip, like fluids or maybe units or other things, like even you can skip a little bit of modern here and there, or you can skip a little bit of thermo, but you can't skip all of these. Few topics definitely you can skip, definitely. Okay, is it possible to crack JEE without an institution? Yes, it is possible, Hamid, but the competition is so fierce that you will realize that if you are not a part of some institution, you feel those drawbacks. You don't know what is the competition. So that's the reason why you actually join some institution, so that you know what's in the game, what's in store for you, so that you don't get surprised on the final day of the exam. Okay, week quiz Shruti is there. Link is there in the description box. Play that week quiz. It's like a homework now. Yes, KRS, this is for JEE also. Okay. Rihan, advanced paper pattern will be obviously tough, and nobody can tell you the pattern right now because it's all a surprise. Okay, fine. Let's move on. Jermia, I think some ray optics. I read your comment. Let me just find it out where it has gone and I'll post it, okay, in case you want it. Oh, Jamesburg, you are from America and you are going to write the JEE exam, Jamesburg, if I'm not wrong. And by the way, the news is like, you can give JEE advanced exam, JEE exam from many countries. In fact, I read an article which said around 25 countries. I hope I'm correct. And so there are going to be a lot of international participants for the JEE exam. So it's going to be really crazy, guys. Okay. And there are a lot of IITs also which are going to be opened up in different countries, starting with the UAE. Yes, there is going to be an IIT which is going to be opening up soon in the United Arab Emirates, and then you are going to also see maybe more countries later on. Yeah, sure, Venkat, definitely. Is it easy to achieve top ranks? Yeah, Sujata, it's not easy, obviously. And all your doubts I'll answer on Saturday 7 o'clock with the not motivational session, the casual talk session at 5 o'clock, motivational session at 7 o'clock, Saturday, this Saturday. Let's begin with the class. And let me change from Superman to the normal role. Okay. So, all right, let me put on my specs. Okay, so there we go. Mind map for your magnetism, effects and sources. Now, this chapter has two parts, and whenever you see a problem, you will see that the question might contain one of these two parts. The first one is sources of the field. The second one is the effect of the field. When I say sources, it means a bar magnet can produce magnetic field, or a current carrying wire can produce magnetic field. So a permanent magnet like bar magnet, horseshoe magnet can produce magnetic field, or an electromagnet, that is current carrying loops or wires, can produce magnetic field. And there would be questions like, what is the field at this point? What is the magnetic moment? What is the pole strength? Those kind of questions can come from from sources. In the effects part, you will see that this magnetic field interacts with charges or currents or magnets, basically charged currents or magnets, and it will produce some effects like force or torque or energy. So that's what we are going to talk in the second half. And there could be some questions which could be a combination of both effects as well as sources. So something generates the field and it also affects some other part of the circuit or the device. Example, two parallel wires carrying current. Two parallel wires carrying current. What do you think will happen? Will they attract or will it be repelling? Good evening, nice to see you, Krishna. Hi, Rian. Well, Rian, I'm pretty sure you'll be bigger genius than me, and I hope that you get into IIT and all your top colleges. Repel, attract, well, it depends. Hi, Vandana, nice to see you. And let's see. Well, Vandana, you should also tell your 10th standard kids I'm conducting a casual talk session at 5 o'clock Saturday. Okay, it depends, guys. It completely depends, because if the currents are in the same direction, then similar wires will repel? No, they will attract. It's exactly opposite of electricity. In electricity, positive repels. In magnetism, same will not repel, it will attract. That's how it is. Whatever happens in electrostatics is on the opposite or on the contrary side in magnetism. If you notice, the Coulomb's constant in electrostatics is 1 by 4 pi epsilon naught. In magnetism, the constant becomes mu naught divided by 4 pi. So epsilon permittivity was below. For magnetism, it is on the up, in the top numerator. So you can see it's always upside down or opposite. Okay, that's how it works usually in magnetism. Okay, so having said that, hello Aisha, hi Ram, hi Deepa, hello Sairam, hello Grishma, welcome aboard. Having said that, if I have two wires which are oppositely placed carrying currents, one is going like this, the other is going like this, opposites in electricity will attract, but in magnetism they will, write it down in the chat box, obviously they will, what will happen? They will repel. No, Niveta, it might not be enough. You will have to go to the detailed classes. You will get a decent or good idea about the chapter, but to get a much better idea, you will have to go through some detailed concepts from the playlist available in the channel. Yes, they will repel. Okay, having said that, let's talk about the mind map. Why is a mind map necessary? It's important to revise the concepts. Maybe you might not remember all the formulas, maybe you don't remember the concepts, the theory, the facts, etc. When you revise through the mind maps again and again and again, you will make a map in your mind, and that will stay in your mind, it will be imprinted in your mind, and that's when you do not blank out or forget those concepts in the exam. Revise it without seeing again and again. So let's talk about field, then we'll also talk about electromagnets, then we'll also talk about the effects, and then we'll also move to the magnetic dipole concept. And the good thing today is that I have already, made those notes for whatever concepts I want you to learn and, what I want to teach. So you will see all these formulas, concepts in the slides coming up ahead. All my handwritten notes, okay? So let's start talking about the field. And the first guy, the experiment which was conducted to figure out that yes, a current carrying wire produces magnetic field was given by, put it up in the chat box. Put it up in the chat box. Yes, you Vandana. The chapter weightage is decent. I mean, electromagnetism as a whole has having a very good weightage. Yeah, at least some 15 to 20 marks at least. Okay, yes, it's going to be Oersted. Yes, Venkat, definitely. I told you already. It was Oersted. And the formula for a magnetic field, due to a current carrying wire element was given by Biot-Savart's law. So Biot-Savart's law is all about finding the field due to a small element, a small part of the wire which carries some current at some distance. And what was that law? Let's have a look at it. So this is the, before that I need to also talk about the field properties. I'm so sorry guys. So let's talk about the field properties and then we'll go to Biot-Savart's law. So if you notice that there are certain similarities in magnetic field properties and also some differences in the field properties if you compare electric field and magnetic field. First, let's talk about similarities. If you talk about similarities in the fields, you will realize that number one, if you have a field, be it magnetic or electric, the tangent drawn to the field line gives the direction of the field. So tangent drawn gives the direction of the field. The second one is that no two field lines can ever intersect each other. They can never ever intersect each other. That's the second thing. Or else you will have an ambiguity. You cannot decide where is the field exactly. The third thing is that always you will see that the field lines wherever they are crowded, that's where the field is very strong, and wherever they are very sparse, less dense, away, there the field is going to be very weak. These are the three similar properties. But there is one property which is quite opposite or different from electrostatics and magnetism, and that is how they start and how they end. Hello Yuvashri, welcome aboard. In electrostatics, the electric field lines originate from dash, fill in the blank, and the electric field lines terminate at dash, fill in the blank. In electric field, starts from dash and terminates at dash. What is that dash and dash? The fill in the blanks. Yes, it always starts from a positive charge and always ends on a negative charge. Very good, Dalchan. Excellent. Hi, Satish. Positive to negative. Very good, PL. Aarti, you're not very late, but you can definitely catch up. You'll probably miss some 5-10 minutes. That's all. Okay, talking about the next point. Yeah, don't worry, Aarti. We are going to see some questions on magnetic force as well and the theory also. Now, having said that, in magnetic field, you will see it never starts from anything or ends at anything. Although many people think, oh, magnetic field lines, I know they start from North Pole and they end at South Pole. That's completely wrong. That's a wrong property of the magnetic field. Keep this in mind. It completes a loop and they are always closed loops. It feels as if it starts from North Pole, but technically speaking, the loops continue even inside a bar magnet. So let's talk about the properties now. So first property I told you, it is tangent. Second property, they cannot intersect. Third, it's strong over here. It's weak when it is less dense. And magnetic field lines are always closed loops. It feels as if it originates from North Pole, but technically the field lines continue even inside this magnet, like you can see over here. Okay, like you can see right now over here. Is that clear, guys? So this is our magnet. So even inside that magnet, you can see that it continues. Now, having said that, let's talk about unit of magnetic field, which is Tesla. You should know this. Usually a Tesla is a very huge unit. The magnetic field of Earth is in millitesla and stuff like that. So it's very, very small. Okay. Bar magnets is maybe around 10 to the power minus 2 Tesla and all of that. Okay. So guys, yeah, you're going to get all these handwritten notes in the Telegram channel. So ensure that you are a part of the Telegram group and make sure you download it as soon as the lecture is over. Okay, Rihan, probably I'll answer the question later on little bit. Okay, now this is very important. Observe this carefully. Closed surface. Closed surface is also called as dash surface. Try to recollect the word from electrostatics. Any closed surface, which is not open, no opening, nothing, is also called as a dash surface. Fill in the blank, guys. I want to see if you can revise this. Yes, Satish, it can go in 10 to the power minus 5 order also, depends. Gaussian surface, very good, Kirtana. Now, if you take electrostatics chapter, a closed surface flux gives you how much charge is enclosed inside divided by epsilon naught. But in magnetism, that's quite opposite. You will see that if you take the net flux of a closed surface, it will always be zero. And there is a very simple explanation for that. Why? Because if you take a closed surface, the blue one, you will see whatever lines are entering in are the same lines which are exiting out. So the number of lines entering in is equal to exiting out. Hence, you will notice that the net flux is zero. Hence, net flux is zero. I hope this is clear. Hello, Om, welcome. Yeah, very good. Next point. Whenever you take a closed surface, there will be some lines, field lines which are entering in, some lines which are exiting out. Tell me the sign of it. Those field lines which enter in, are they going to be positive flux or negative flux? Come on, answer in the chat box. Let's see how many of you can remember this. If you take a closed surface and some field lines are entering in, what do you think is the sign of that flux? Is it positive or is it negative? Think about it. And the field lines are basically going to enter in. Come on, let me know. Shruti saying positive. Satish, the paper discussion was already over. I think it's done. Let's focus on JEE now. Okay. Yep. Minus to plus. Minus and plus. Okay. Plus. Okay. Whenever field lines enter in, keep this in mind. In is basically negative. Out is basically positive. Now, if you find it tough to remember, I'll tell you one simple fact. If you take a negative charge, what happens? Field lines charge, electrostatics, not magnetism. Field lines always enter and terminate on that. So if they terminate on that, negative charge will create negative flux, right? Try to recollect Gauss's law. Negative charge will create negative flux. Positive charge will create outward flux. So outward flux is positive. Outward flux is positive. Inward flux inside is negative. That's how you're going to remember it. Is that fine, guys? Very good. Excellent. So negative is inside, positive is outside. Keep this in mind. Very good. Okay. Now, electric flux or any flux in general, what does flux tell you? In general, any flux tells you the flow of the field. It tells you the flow of the field. How much field is flowing in that area. Electric flux was electric field into area through which it is passing. Electric flux is electric field into area. Same way, magnetic flux will be the magnetic field into the area, but there is again a dot product as usual. If you want to get rid of the dot product, the magnitude will be BA cos theta, where theta is the angle between the magnetic field and the area vector. So if you have an area like this and magnetic field is this way, so this is theta. So this BA cos theta gives you the magnetic flux. Now the unit of flux is basically Tesla, because B is in Tesla, I just told you, into meter square. This Tesla meter square is also called as Weber. 1 Weber flux is when 1 Tesla field passes in 1 meter square area. Okay, I hope this is clear. All right, great. This is very important. So I've discussed a lot about flux till now and the field properties till now. Okay, so this much is done, and we have also discussed about the flux part. Now let's go to some permanent magnet theory also. A permanent magnet is nothing but a object which always shows some property of magnetism. It has some field lines around it. There is no need of current to be supplied. A bar magnet, horseshoe magnet, these are the best examples. And there is one special thing about any magnet which is quite different from electrostatics. In electrostatics, you can take a positive charge, you can take a negative charge. You can take how much ever positive you want, you can take how much ever negative you want. But in magnetism, it's always buy one, get one free. Meaning, if you have a north pole, you will always get somewhere an equivalent amount of south pole. In electrostatics, you can bring Pandu separate, Champa separate. Pandu separate, Champa separate. But in magnetism, Pandu always comes with Champa. They are a couple. Both the polarities come together, always. Hence, magnetism, you always see dipoles, two poles together, but opposite. Hence, it is called as a dipole. Look at this is a bar magnet. There is a north pole over here. You can see that there is a north pole over here. There is a north pole over here and south pole over here. Always comes in pairs. Now, this magnetic dipole, or basically any magnet, will obviously create some field around it. You can see that. And this magnet has two important lines which you should know. Unit of magnetic flux is density. Flux density is flux per meter square. That will be Tesla Krishna. Okay. So flux density Tesla meter square by meter square will become Tesla. So it will be field. Okay. The two important lines are axial and equatorial region. Axis is the axis of the magnet. So if you join north and south pole, you get axis. Equator is the perpendicular line. Very important pointers right now over here. Okay. Now there could be questions where you cut a magnet along the axis or you cut a magnet along the equator. We will deal with that separately. That's why I have told you about these two important lines. Now, whenever you take a bar magnet, like I said, there are two polarities. The strength of that pole is also called as the magnetic charge, which is also called as a pole strength or a magnetic charge. See, an electric charge creates electric field. A magnetic pole or magnetic charge creates magnetic field. Technically, you cannot find this magnetic pole. It's just in your head. It's just a concept, because nobody can get a north pole separate or south pole separate. It's just for your understanding. The north pole is considered as plus m. The south pole is considered as minus m. The small m is not mass. It's not mass. A lot of people get confused. It is a magnetic charge. Yes, Jaya Jagya, we'll be talking about it. Okay. All right. Great. Everybody clear about this? Okay, moving on. Now, electric dipole, minus and plus, minus q plus q, separated by distance L, created electric dipole moment. I hope you remember this from electrostatics. Minus m and plus m, minus m and plus m together will create negative charge and positive charge creates dipole moment, but in this case it will be magnetic dipole moment. Magnetic dipole moment. Got it? And if you recollect, yes, we are going to discuss questions, Satish, but always theory first. Electric dipole moment was charged into the separation. Charge into separation. Magnetic dipole moment will always be the magnetic charge into the separation between them. This separation is called as the magnetic length, the distance between the two poles. Generally, it is given in the question. So it is L. So M into L is magnetic dipole moment. All right. Everybody clear till this point? Hi, Pugal. Welcome aboard. Okay. Now, you only tell me, if I cut the magnet along the axis, will the magnetic dipole moment become less or more? Put it up in the chat box. Yes, it's very easy. That's why I'm training you to learn this in comparison or analogous with electrostatics. It becomes easier. When you cut a magnet along the axis, will the magnetic dipole moment become less or more, or will it remain the same? PL says does not change. No change? Think again, it will change. A lot of you got it wrong. See, this length and this length is the same. Yes, the length remains the same, obviously, because you can see that you are cutting it along the axis. So this length and this length is the same, but you are cutting the pole into half. You are cutting it, so the pole strength reduces. Be careful. So you are cutting the north pole or south pole into half, so the pole strength reduces. In turn, it will reduce the magnetic moment. So when you cut it along the axis, the magnetic moment reduces because the pole strength is less. Got it? Everybody with me? Now, what will happen if you cut it along the equatorial region? Now you can see that the length becomes half length, or depends where you cut it. But the pole strength will remain the same. Whatever north pole was here, the same north pole will come over here. So magnetic pole strength is the same, length reduces. Hence, the magnetic moment reduces. So either case it reduces, but you should know because of what quantity does it reduces. So along the axis it reduces because of small m, that's the pole strength. Along the perpendicular bisector or equator, it reduces because of the length itself. Hi Nikita, good evening. Got it? So these kind of questions can come. Okay, I don't know, I will not go to white screen because a lot of students wanted the black screen. It's good on the eyes, plus it's good for me also. When I see that bright white screen, what happens is, my eyes start burning. So that's the reason. Plus, it's also good for your eyes. That's why I'm using dark mode. And plus, I think things look a little bit more clearer apart from the minor reflections of the room here and there. That's okay. Yeah, I'm going to stick with black. Don't worry, guys. Okay, now moving on to the next concept of Biot-Savart's law and Ampere's law. Let's move on to that. Oh, no problem. I don't know. It's okay. You can ask. You are free to ask anything. Now, Biot-Savart's law and Ampere's law are very much related. They are used to find out fields due to different geometries. So let's have a quick look at both of them. So if you take an element right now over here, this is an element which is carrying some current I, and you are over here at some position vector r, then at this point the field direction is given by dl cross r. So dl is the length of the element in the direction of current cross r. So hold your right hand, take your right hand like this, point it in this direction and then cross it with r. So dl cross r, it goes inside, hence the field will also be inside the plane of the board, like you can see. The magnitude is mu naught by 4 pi I dl cross r divided by r cube. That's the formula for Biot-Savart's law. The value of this constant is 10 to the power minus 7 standard. Now next thing is Ampere's law. Okay, yes, I'm going to discuss those BitSat and UG questions as well after just maybe few days, maybe from June, where that's when the bits and all these exams come close by. Now if you talk about Ampere's law is an extended version, or you can use it like a substitute sometimes because it's easier to find out the field in certain cases, and it's also very similar to Biot-Savart's law except for the fact that it makes the job a little bit easier. Now according to this law, magnetic field dot dl vector is mu naught into I enclosed. Let's talk about it. Don't get so nervous about the diagram. Okay, so what we have is 4 wires. Okay, I1, I2, I4, I3, these are the currents in the wires, and I choose a path around some wires. This is the path, the blue line that you see, it's a closed path. That means I start at a point and I come back at the same point. Now if I talk about any point and if I calculate the field at that point, the field at that point, will it be because of only I1, I2, or will it be because of I4, I3, or because of all the currents? The field at any point on this blue colored path, is it because of any one specific current carrying wire, or because of all the currents? Think logically. It's always because of all the wires. Each and every point will experience magnetic field due to all the currents, no matter how far, no matter how close they are. But there is one interesting thing which will happen. If you take magnetic field dot dl, at this point magnetic field dot dl, at each and every point you take B dot dl and you sum it up. So B dot dl, and you sum it up for that closed loop. Summing means integration, and because you're coming back to the same point, it's a closed path, hence I'll use this cyclic integral. So this is because it is a closed path, and integration stands for addition. You are adding up all those things. You will see that their sum, so B at every point dot dl at every point, their sum on the closed path comes out to be mu naught into the enclosed current. That's how it is. And if you compare it with the electrostatics, in Gauss law, the surface integral of electric field dot area always used to be charge enclosed divided by epsilon. And what did I tell you about electricity and magnetism? If in electricity epsilon is below, in magnetism mu will be on the top. So you can see it's very much similar to electrostatics as well. Okay, having said that, you will see that the enclosed current in this case is only the currents which are going in, and those are shaded clearly in green. Yes, it's like exactly like Gauss law. Now the question arises, what is the sign of the current? This is what many people do not know or forget about it. Yes, it's just like electric field due to all the charges in Gauss's law. Yes, correct guys. In charges, the sum of the charges was very simple. If the charge is positive, positive. The charge is negative, negative. You can add positives and negatives. But in currents, you need to know which current is positive, which current is negative. Simple rule, right hand thumb rule. Okay, first take your right hand, take the 4 fingers and turn those 4 fingers in the direction in which you are going around the loop. So I'm going around like this. So curl your fingers this way. Curl your fingers this way. See where the thumb is going. The thumb is going up. If the thumb is going up, all the currents in the direction of the thumb are positive. All the currents opposite to the thumb are negative. So I1 is in the direction of the thumb, so positive. I2 will be negative because it's going opposite. That's all. You will not consider I3 and I4. As simple as that. Is that understood? So right hand thumb rule will give you the directions, the signs of currents. Fair enough guys, can we move ahead? Okay. Fleming's left hand, right hand. I don't like Fleming guys, I mean like really. Please ask him to like go bye-bye because it's crazy. Left hand rule works, right hand rule, Fleming's works for EMI when perpendicular, but when it is not, then it becomes really confusing. What will you do? Will you act like a crab in the exam? Oh, Fleming's left hand rule, oh there is magnetism, oh there is EMI. The teacher, the invigilator will think you guys are crazy. Just use right hand guys. That's it, only one right hand. Okay, moving on to the next one. So next we are going to go to the different geometries and their field formulas. Yes, me too. I am pretty sure. Yes, Krishna. So forget whatever you learnt in 10th. Okay, it's not needed. Just right hand rule, nothing else. Every time cross product. Do you know why you studied Fleming's left hand rule and right hand rule in 10th? There's only one reason for that. Because you did not know about the cross product. You did not know about vectors and how to multiply them. That's the only reason. Once you know the cross rule, you know how things work. That's the reason why cross rule was invented, so that you don't have to remember Fleming's left hand rule, Fleming's left foot rule, Fleming's foot in the mouth rule, Fleming's left ear is on the neck rule. So many things, unnecessary confusion. Okay. If you have a long wire and it produces magnetic field like this, and how do I know it produces it like this? Again, right hand rule, Zindabad. That's all. So take your right hand. What is straight? The wire is straight. And out of these two things, my fingers and my thumb, obviously my thumb is straight, obviously. I mean, so put your thumb in the direction of current. Your fingers will curl. So the direction in which the fingers curl gives you the direction of the field, obviously. The formula is mu naught I by 2 pi r for a long straight wire. As simple as that. Okay, ring formula I tend to forget. Hold on. I'll make you remember that also. Similarities are there in electrostatics and magnetism. Now, by the way, this formula is very similar to a long wire which is uniformly charged. Try and recollect mu, instead of mu naught by 2 pi, it was 1 by 2 pi epsilon naught, and instead of current you had lambda and here r. Isn't it similar guys? Isn't it similar guys? Yeah, very similar, right? Okay. So very similar to electrostatics, uniformly linearly charged density lambda. Yeah. But if it is a finite wire, yes, it's infinite wire. If it is a finite, that means the ends of the wire subtend certain angle. So this is the perpendicular, here it is alpha, and from below it is beta. So if it subtends certain angles alpha, beta, then the formula changes. Mu naught I by 4 by r. 4 pi, notice this 2 becomes 4. Sine alpha plus sine beta, again similar for a finite wire. Same formula was there, guys. I mean, this is ridiculous. I mean, it's the same thing. Yeah, it used to be like 1 by 4 pi epsilon naught lambda by r sine alpha plus sine beta. Very, very similar. So when you study it in tandem, comparing, it becomes easy. Like, I know this. If you study it separately, then you'll be like, oh, what is this? What is that? So many formulas. No, it's similar. Okay. Having said that, let's go to the ring formula, everybody. Oh, when do we take angle positive and negative? Okay, so basically, imagine this. Oops, let me just show you. So let's say over here, this is 60, this is 40. So in this case, alpha will be 60, beta will be 40. Example, I'm just putting some random angles. Now, imagine this. There is a wire here and you are here. Now this is the perpendicular. This end is one angle. Let's say this is, I don't know, maybe 60 degrees. And maybe I'll just put another angle over here. Oops. This angle. And let's say this is 30 degrees. Now tell me what is alpha and what is a beta. Clearly. Come on. This is one end. This is the other end. Clearly tell me what is alpha and what is beta. Alpha is one extreme. So clearly alpha is going to be 60 degrees. Now your beta technically is measured on this side of the perpendicular. Beta technically is measured on this side. But this 30 is on the other side. So it is negative of the side where beta exists. So hence beta will be minus 30 degrees. That's it. That's all. Krishna, using right hand rule. Okay, why is the field going inside? Right hand rule. You use the thumb in the upward direction, fingers curl like this. If you see on this side, it goes in. If you come from the other side, that is here, it comes out. Comes out, goes in. I hope that is clear. Hi Bobby, nice to see you back. Got it, my warriors? Yep, very, very important. All right. So this is crucial, guys. If you have any doubts, please feel free to ask, sir, how to use this formula. That's why you are attending a live class. I'm your teacher. I will be happy to help you and remove all the confusion. Don't worry, we are all going to learn here. You can make mistakes, you can ask stupid but relevant doubts. Don't ask, sir, tell me about black holes, some radioactivity, God knows what. So please ask me relevant doubts now. Okay, talking about the ring carrying current or wire loop carrying current, I, radius r, C is the center. So again, finding the direction of the field using right hand rule always, Zindabad. So what is turning? Current. So take your four fingers, turn it in the direction of the current. The field will be in the direction of the thumb. I hope this is clear. Okay, so that's why the field is here at the center. And this field is mu naught I by 2r. Now many students get confused between this formula and this formula, because the only difference is pi. Here there is no pi, here there is pi. It's very easy. I'll give you a simple trick. Usually, if you have a straight wire, field lines are circular. Circle means perimeter thing, 2 pi r. So when you have a straight wire, the magnetic field is circular, so 2 pi r. That's all. In this case, when the current is circular, field is straight. You can see the field goes in a straight line. So no pi for it, no cake for it. Sorry, birthday party pi is here, no birthday party pi over here. I hope this is clear. Oh my God. Thank you, Bobby. Bahubali. Okay. Except for the fact that there is no Anushka. Hai na? All right. Now, moving on. This is x distance away from the axis. On this point, the magnetic field will be given by mu naught I. This whole formula r square by 2, this thing. Now, how do I remember it is because if I substitute x as 0, I should get this answer. Because if x is 0, this point will come here. So I know if I substitute x 0, I will get that 2. So that 2 is here and rest all is simple. And this is very similar to the Electric field of a charged ring, it was, 1 by, what is it? K, Q, then X, and then you had R square plus X square raised to 3 by 2. So something raised to 3 by 2 was there, I remember. So in this formula also, R square plus X square raised to 3 by 2 will be there. Yes, you can remember it in terms of cos theta also. Okay, I hope this is clear. I see cross and dot. What does it mean? Shruti, cross means in, dot means out. It's like your Bahubali guys. Who was that guy? Bobby. So imagine Bahubali, Anushka being trained by Bahubali. Arrow is going away from you. What will you see? You will see cross. Arrow is coming towards you. You will see dot. That's what it is. Okay. Now, if you do not have a complete loop, if it's an arc, then it's going to be very simple. See, due to a complete loop, it is this much. If it's a part of the loop, it will be exactly contributing that much fraction only. So theta by 2 pi is the multiplying factor, like you can see right over here. Why theta by 2 pi? It's a fraction. If it's a semicircle, the semicircle will have only half the contribution. So angle will be pi divided by 2 pi, which is half. If it's a quarter, it will be 1/4. So you just take that much contribution, because one circle gives this much, a part of it which subtends theta will give only this much. That's all. I hope this is clear. Okay, I hope this is clear. Now moving on to the next geometry. So guys, we are now over here, we are talking about the applications. We are going to find the fields. We are discussing the formulas for fields for different geometries. Okay, we are on the mind map right now. There is one more important formula which you should know for a long wire. When you take a long wire carrying current, it not only produces field outside of it, it also produces field inside of that wire. This is the formula. Outside, mu naught I by 2 pi r, same formula which I just gave you. Same formula. Mu naught I by 2 pi r. This is the field which is created outside the wire. But even inside the wire, you will see there will be field. If you are at some distance from the center and r is the radius of the wire, inside, when you are inside, look at this, r less than r is when you are inside the wire. The formula is this, mu naught I 2 pi instead of small r, that small r goes on the top, divided by r square. In fact, if you draw the graph, you would have seen this graph many times. The graph comes like this. It comes like this. Here it is proportional to r, here it is inversely proportional to r. This is how the field varies. It is 0 on the center. It starts from 0, maximum, and then again reduces. Keep this in mind. Okay, I hope this is clear. Okay, fair enough. Okay, so let's move on. When will I start JEE 2024 batch? Well guys, already the JEE 2024 lectures are available for all of you. Who was asking it? Jayanti, Rohit. It's called as a nurture series. It's there in the playlist, 11th standard, physics, chemistry, maths. So you can start watching. Everything is beautifully arranged. Don't wait for live classes. Start watching those classes only. Beautiful classes. But I will be conducting more revision and problem solving classes. Don't worry. Okay. Simply Wolf, I'm not sure, Bacha. You should ask Shimon sir. But I think he will. Okay. Solenoid. For solenoid is nothing but a coil which is wound. But the coil has different planes. It's not just a loop. So that's the difference. In a loop, the plane of the coils are the same. In a solenoid, the coils are wound in different planes. You will see that the field will be produced like this. Inside, the field is uniform. It's roughly constant unless you are towards the edge. So it is basically almost uniform. That's why you can see the spacing is roughly the same. There's a long solenoid. And it is mu naught n by L I. What is n? Turns. What is L? Length of the solenoid. N by L, turns per unit length. Outside the solenoid, the field is 0. Outside it is 0. Okay. Pugal, you can leave a comment after the session is over. I'll definitely help you out with that. Bobby, for KCT, use the crash course. Now toroid. Toroid is an extension of solenoid. See, solenoid is straight. Coils are wound one after the other. If you take the solenoid, the ends of it, the fields are coming out. You can see the fields are coming out. If you take those two ends and merge them together, you will get a toroid. So the fields which were escaping, they will no longer be able to escape, they will only go inside the toroid. And because the toroid is an solenoid which is bent, the formula for the field is exactly the same. Look at this. Magnetic field inside the toroid is mu naught n by Li. Same formula, but keep this in mind. Here, this was the length of the solenoid. When you bend it, the length will become the circumference of the toroid. So the circumference will be 2 pi r. That's it. I hope this is clear. What if the radius of the solenoid is comparable to its length, Himanshu? If that's the case, then you will be using this formula. Let me just put it up over here. There is a formula like this. Okay, let me just write it. This is our solenoid. Okay, and let's say you are at this point. This and this are comparable. So what you do is basically draw two lines, construct two lines, draw a perpendicular. This angle is alpha, this angle is beta. This angle is alpha, this angle is beta. Okay, so the magnetic field at this point will be given by similar formula. So mu naught n I by L, but just put a 2 over here. Just put a 2 over here, and this alpha and beta, you can measure it if all the values are given. So it will be nothing but sine alpha plus sine beta, just like a finite wire. Very similar to finite wire. So you put 2 over here, and that's how you get it. In fact, for an infinitely long solenoid, alpha and beta will be 90. Alpha and beta will be 90. Sine 90 is 1 and 1. 1 plus 1 is 2. 2 cancels, you will get this formula. That's it. I hope this is clear. Is that understood? Toroid and solenoid difference. Toroid is round, solenoid is straight. Solenoid which is bent so that the ends meet each other is a toroid. That's it. Infinite application, as in, imagine radius is in centimeters or millimeters and the length is in meters or many centimeters. That's how it is. Fair enough, guys? Understood? Clear? Yes, definitely, Tushar. In fact, not 100 plus, 150 plus. The reason why I'm conducting these sessions is so that you can score high. It's 0 to superhero. What it means is what it does. Okay, let's move on. Okay, so now we'll go to the effects. So we have done a lot of things over here. We have done a couple of things over here. Now we will also talk about the effects of magnetic field on different charges. Will there be any force or torque and energy, and also the galvanometer concept and how it can be used to make instruments. So let's talk about that, and then we'll come to dipoles. Okay. If you take a charge and you place it in electric field, it experiences electric force. Only from these sessions? No, Tushar, you have to obviously practice. How is it possible? Think what you are saying. If some teacher has told you that only watching my lectures will give you 100 plus, for sure he has fooled you. I am not the person who is going to fool you. I'll tell you the truth. I don't know, listen to me, fine. Or you feel that no, some teacher told on YouTube that watch my classes, guarantee 100 plus. Go ahead, for sure. Okay. Okay, thank you, Himanshu. Thank you, Jay. Solenoid and toroid, oh my god, there are so many examples of solenoid and toroid. It's basically used in transformers. Transformers at the end of the day is a solenoid. It is also used to make an electromagnet. It's also used where you can change the current's direction and you can make your phone's vibrator. Yeah, it's at the end of the day solenoid only. Okay, practice questions are coming, Ishika. Hold on, first theory. Few more minutes and then we are coming to questions with PYQs. If you take a charge, place it in a field, it experiences force. It experiences force. Force is given by QE, charge into field. If you take the same charge, place it in a magnetic field, it will not experience force unless you throw it or move it. Only when it moves does it experience magnetic force given by QV cross B. So major difference is electric field's force is not dependent on the velocity, whereas magnetic field's force is dependent on where and how much you throw it. Number one. Number two, the force is always going to be in the direction of field or opposite to the direction of the field. Oh, why can it be opposite? Can you guys tell me? How can the force on the charge be opposite to the field? Think about it. Good evening, Kalai. Hello, IS Sami. Hello, Abhi. Welcome. When can it be opposite? When the charge is negative. This is a sign sensitive equation. Q is positive. Yes. Force is in the direction of the field. Q is negative. Force is opposite to the direction of the field. Keep that in mind. Yes. Very good, PL. Excellent, Shruti. Very good. Very good, Jay. Very good. Very good, Kalai. All right. Now, moving on. Here, also this is sign sensitive. If the charge changes, the force will also change the direction. And this is a cross product, so always use cross rule. So take your right hand, first place it in velocity, then magnetic field. You cannot go like this, it's a long way. Go the short way, V cross B, so it will be down. V cross B, always. Third thing, you will see that force, because it always acts in the direction of the field or opposite for electric field, for magnetic field, it is always going to be perpendicular to the velocity. Never, no matter how you throw, it always acts perpendicular to the velocity. Keep that in mind. And it's also perpendicular to B. That's simple cross product. C is A cross B. Naturally, C is perpendicular to A. C is also perpendicular to B. That's simple cross rule. Because of this fact, because of force being perpendicular to the motion, it creates a very nice effect. And that is, the work done by that force will always be zero. But that's not true for electrostatics because the force can be in the direction of motion also. So electric force can do work. Electric force can do work, but magnetic force will never ever do work because it is perpendicular. And because of this concept that it does not do any work, by work kinetic energy theorem, it cannot even change the kinetic energy. It can't change the kinetic energy. If it can't change the kinetic energy, obviously it can't change the speed. So a particle thrown in magnetic field will never ever change speed, no matter how strong the field is, no matter how strong the speed is, no matter how strong the charge is. Keep this in mind. But yeah, direction, yeah, definitely, because force is perpendicular to motion, just like your circular motion. Force perpendicular to displacement, direction changes. So direction can be changed, speed never changes. Okay, now moving on to the next one is here. When you take a charge and throw it, it experiences forces. Same way, a current carrying wire also has charges moving in it. A current carrying wire also has charges moving in it. Hence, can I not say a current carrying wire also should experience force? And that's what it is all about. A current carrying wire, I, length L, placed in magnetic field will experience the force IL cross B. That's something which you should keep in mind. L cross B. No need of rules. Fleming's left hand, right hand, not needed at all. So IF is equal to IL cross B. Okay, that's something which you should know. Now, if the wire is not straight, if it is a curved wire, then remember there is a shortcut to this. And the shortcut is when the wire is curved, you can replace it with a straight wire. So the force on a curved wire is always similar to the force on a straight wire, and the formula becomes IL cross B, where L is just the effective length. It's very easy to solve the question, especially for bent wires, like a curved wire, like a semicircle, quarter circle, connect it with a straight wire. What if you take the two ends and join them together? If you take the two ends and join them together, effective length will become 0. So for a loop, you will see always the net force is 0. Ranveer, if the magnetic field is not constant, then these two properties do not hold true. These properties are always true when the magnetic field is uniform. If it is not uniform, then you will have to integrate it. Force is integral I dl cross B. Yes, always integration comes when things are not uniform, not constant. Okay, I hope this is clear. Very good. I hope, Ranveer, that is clear. Let's move on to the next point. Okay. Now, there are 4 different cases which you must know for the path, the trajectory, and how the field is aligned with the velocity. First case is actually, I've not even put it over here. If the velocity is parallel to the magnetic field, or I think I put it there. If velocity is parallel or anti-parallel to the field, then you will see that the V cross B quantity will be 0. So there will be no force, hence it will move in a straight line, hence velocity will be constant. As simple as that. If V cross B is 0 when it is parallel or anti-parallel, because sine 0 or sine 180 is 0, you will see it will not change the velocity neither in direction nor in magnitude. It just continues its motion along the field. Simple. If velocity is perpendicular, here it was parallel, here it is perpendicular, then the force will always act perpendicular and it will go in a circular path. It will perform uniform circular motion. Radius is mv by qb, time period is 2 pi m by qb. Keep this in mind. Okay, I'm very good, Jayashri, thank you so much. Okay, will there be a situation of varying current in the conducting wire and placed in a magnetic field, then force experience? Yep, there could be for advanced, but for mains, no. Okay, now moving ahead. So radius is mv by qb, time period is 2 pi m by qb. You should know these formulas, direct questions come from this. The third case is when you put the velocity at an angle with the field. Velocity is here, field is here. The velocity will have two components. Parallel to the field, v cos theta. Perpendicular to the field, v sin theta. This component, the one which is parallel, will never change, it's constant. I just told you. The one which is perpendicular, here, it makes it go in a circular path. So perpendicular makes it go in a circular path. Parallel component will not affect it, it will just go in a straight line. So because of this, if it goes in a circle, and because of this, if it goes in a straight line, the combination of these two will make it go in a circle progressing forward that looks like a spring motion, which is called as a helical motion. Helix. I hope this is clear. Understood, guys? Very important. Now, when you talk about a helix, there are two properties of a helix. One is the radius of that helix, which is also the radius of the circular path. The second is how far are these circles from each other, one after the other. That's called as the pitch of the helix. Meaning, if the charge starts from here, goes around and comes back on the same line, how far is this point from this point from one rotation? That's called as the pitch of the helix. So pitch is whatever this velocity into the time period. This velocity, this constant into one time period. That's 2 pi m by qb into v cos theta. Radius is simple. Circular motion's velocity will come here. You can see same formula. mv perpendicular by qb. As simple as that. Okay. Kind of enough, Abhi, but you will have to dwell into more concepts. So this is more like one shots. Remember, for deep concepts, there is no possibility you can cover it in one shots. You will have to go through HCV or detailed classes. Okay. All right. Cool. Let's move on. And JEE means which topic takes main role in scoring? I'll probably tell you, Jayashri, if you put it as comments later on. Okay. Last case, cross field. Cross means perpendicular. But this is a special case where velocity is also there, magnetic field is also there, electric field also is there, and three of them are mutually perpendicular to each other. Electric field is down, so a charge will experience force downwards in the direction of the field, assuming it's positive. It's also thrown perpendicular to the field. Electric field is down, velocity is perpendicular, V is there. Magnetic field is inside, so you can see velocity, field and other field, all three are mutually perpendicular to each other. V cross B comes up, force due to magnetic field is in the upward direction. In a very special case where this force cancels out this force, the force down and the force up cancels out, there will be no net force on this charge. It will not have any kind of acceleration or deviation, so it will not get deflected. It will just move straight. So QVB, magnetic force, will be QE, which is the electric force. QQ cancels, V will be E by V. That's the condition for no deflection. If by chance any of these parameters change, like field or velocity, you will see that the charge will either deflect this side or this side depending on which force is higher. If this force is strong, this is weak, it will go this way. This is weak, this is strong, that way. This can be used to separate out particles based on their speeds. Very, very important concept of crossed field. Okay, V is E by V, very important concept. Okay, now we are going to go to dipoles, guys. So in the mind map, if you see, we are going to come to dipoles, and then we'll also talk about the measuring instruments like ammeter, voltmeter and galvanometer. Okay, this is done. So remember dipoles, north pole, south pole, that's what a magnet is. So a current carrying wire loop also behaves like a magnet. There is a north pole and south pole associated with it, because I can see that if the current is going like this and you curl the fingers like this, you will see your thumb will point in certain direction. That's the direction of the field. And if you take a magnet and you place it instead of this current wire, it will also produce field in that direction. This loop also produces field in that direction. So I can assign north and south pole over there. As simple as that. So since a magnet has a dipole moment, capital M, this also has a dipole moment. There is a calculation for that, and it comes out to be NIA, National Investigation Agency, just like you have CIA in Hollywood movies. In Indian cinema, you have NIA. Okay, you can have RAW, you can have CID also, I know, but NIA, that's how you're going to remember it. Okay, dipole is very similar to electric dipole. Yes, Himanshu, very true. Hello, Sudarshan. I'm so glad and so happy about it, Abhi. Make sure you watch all the classes. Trust me, you will be reaching a next level. No problem, Shruti. Moving on. Here, since we have talked about electric dipoles in electric field, it also makes sense to talk about magnetic dipoles in magnetic field. This magnetic field is not created by the dipole. It's somebody else's dipole, somebody else's field. So taking a loop, placing it in front of somebody else, it will react to it. I just now told you, when you take a loop carrying current and you place it in some external field, it never experiences force, as long as the field is uniform, of course. So if it's a uniform field, the net force on it is zero. So a loop placed in field will experience zero force if it is uniform field. What's the significance of magnetic moment? I'll come to that. Now the torque acting on it, just like it was P cross E, electric dipole moment cross electric field, here it is magnetic dipole moment cross magnetic field. Potential energy was minus P dot E, here it is minus M dot B, dipole moment dot magnetic field. The significance of magnetic moment is that it is one singular quantity which helps us make the calculations. Just imagine if you had an arbitrary shape loop, even circular, each point will experience force in weird direction. Imagine writing the torque of that loop by calculating the forces and then seeing what is the torque of each force and then integrating and finding it out. Same reason why you define moment of inertia. Same reason why so many other things are defined, because it makes the calculation easy. If I had to calculate the kinetic energy of a rotating body, I have to add the kinetic energies of all the particles. Instead, I know of a quantity called moment of inertia. So half I omega square simply gives me the answer. I is already calculated. Same way, magnetic moment, if I know it, I don't have to use my brains. I don't have to calculate it for every single point. Just M cross B or minus M dot B will give me energy or torque. As simple as that. Okay? I'm so glad, Jay. I'm coming to that, Shekhar IIT. Favorite part of physics, gravitation, electromagnetism. Yes, super easy, standard one. So according to these formulas, torque and potential unit is same. How? Anyways, Ranveer, not according to even these formulas. Even general, forget these formulas. Work is force into displacement. Energy is force into displacement, units wise, force into displacement. And torque, R cross F. Energies and torques, dimensions are same. Units are different. Units are quite different from dimensions. Understand? Just because two things have same dimensions need not mean they have same units. Understand? So units are defined as per the physical quantity. Dimensions are just dependent on what other fundamental things they are dependent on. Okay? Okay, understood guys. 0 to superhero series helps. Yes, Monish, why not? Alright, so now we have to move to the last part, which is your instruments. Let's talk about galvanometer first, and then we'll go to ammeter and voltmeter. Forget this part now. Galvanometer. Galvanometer is a device used to measure current. But this device is very sensitive. Like a sensitive kid. You tell him something, he starts crying. Okay. So, what is there inside a galvanometer is there is a coil. In that coil there is current. When you pass current, what will happen? It will develop magnetic moment, just like over here. It develops magnetic moment. And what happens if you place it in front of somebody else? Oh, it will react. There will be a torque acting on it. So, if you take this coil and is placed in a magnetic field, you will see that this coil will experience a torque in front of the magnetic field. You pass more current, there will be more magnetic moment, the torque will be higher. It will rotate even more. Got it, guys? There will be more torque. Now, if there is more torque, it will deflect. And on that coil, there is a pointer or a needle attached. So as soon as you pass more current, the needle will also deflect. If you change the direction of the current, magnetic moment reverses, torque reverses, it will deflect on the other side. If you don't pass any current, no torque, no deflection. As simple as that. Now, you might be wondering, how does it come back? Because once the torque is removed, how does it know it has to come back? Well, there is a torsional spring, a spring-like thing. So, it makes sure that it does not continuously get deflected. So, it maintains the equilibrium. And the moment you remove the current, the torque disappears, the spring will pull it back to zero. So, the spring is adjusted in such a way that it always pulls it back to the equilibrium zero position. That's why I can say angular deflection of the galvanometer is proportional to the current passing through it. Now, there is a limit to it, meaning there are some markings on the galvanometer, and like I told you, it's a sensitive device, meaning if you pass a lot of current, it will start crying. In this case, it will just burst, it will explode, or maybe it will just burn out or catch fire or whatever. Reason is there is a limit till which it can bear the current. After that, it will just get damaged. So there is a limit of the current, and hence there is also a limit of the maximum angle. This maximum angle is the maximum angular deflection or maximum deflection of the galvanometer, and that current is the full scale deflection current. Full scale deflection current. Shreyas Paliwal, for that you watch another lecture, is there. Today I want to discuss only the important parts of magnetism, because those parts are not so, I would say, high weightage. Hence there are one shots, or even my detailed classes, they are self-sufficient. 1 or 2 classes you will understand it. Okay, fair enough, guys. Ishika said force and energy. Force and energy, they don't have same units, bacha. Force is Newton, the energy is Newton meter. Be careful. Okay, now talking about ammeter and voltmeter. Now see, like I told you, galvanometer is a sensitive device. You pass a lot of current, that's it will start crying, it will get damaged. Now, how do you make it? How do you make it respond to high currents? Well, the logic is simple. When you want to pass high current, and you know that galvanometer is very, really, it cribs for everything. Yeah, like you always have a person who always starts cribbing, yeah, for everything. So same way, galvanometer does not like a lot of current, it just starts crying. So what you do is you bypass the current. So you create an alternate path across the galvanometer, so that this high current which is entering inside, only a small part of it enters the galvanometer. Most of the current passes through this parallel resistor, which is called as shunt resistance. This is called as the shunt resistance. Very good, Pugal. Hello, Sonalika. Now, because you are bypassing, most of the current passes through the shunt. That's why I have put shunt current is more than the galvanometer current. So now you have maintained the safety of the galvanometer, it's safe hands, and that small current is enough to sense how much current is actually flowing here. So this is the actual current, a small current flows, that deflection gives you an idea of how much is the actual current. Now this current is this current plus this current according to Kirchhoff's current law. Is shunt resistance always small? Ideally, yes, but yeah, JEE Advanced, you never know, they can just say this is more. So that will be a very bad ammeter, obviously. So a good ammeter should have very small shunt resistance because a lot of current should go over here. Okay. Oh, by the way, what's the ideal resistance of an ammeter? What's the ideal resistance of an ammeter? Liker, H.C. Verma, Irodov, previous year questions, and Tattva material. 4 books, that's it. Enough to get all India rank 1. I'm telling you all India rank 1. I'm not even saying all India rank 100, 1000, 2000. No. All India rank 1 you want? Tattva, H.C. Verma, Irodov, previous year questions. And notes and all those mock tests and assignments are obvious. Those are extra materials. Books wise, which you buy, that's it. Mansi, I will let you guys know very soon what I will plan. Right now, the passing out students need a lot of help, guys, because it's like, they can't afford to lose out on anything. Just think about it. I'll be doing the same thing for you guys next year. And these guys have their exams in the days to come. So we need to put in all, give in all that we have. That's why all my energies are over there. Yeah, ideal ammeter 0. Correct. Very good. Okay. Now, oh my gosh, thank you. Somebody just pointed it out. PL, thank you so much. Now, in case of, can I erase it? Oh, I can't, is it? Okay, I'll just, oh. Thank you. You know why I wrote this? They're in parallel. Do you see both the resistors are in parallel? And what have we learned in parallel circuits? The current splits and prefers less resistance. In fact, currents are inversely proportional to the resistance. More resistance, less current. Less resistance, more current. So IG by IS is nothing but RS by RG. That's my inverse relationship. I hope this is clear. Is that understood, guys? Very good. Deflection is responsible for measurements of small currents out of the total current. Yes. But it is calibrated, Abhi. See, I know the deflection measures the small current. But I know this 1 milliampere is actually 1 ampere. Or 2 milliampere is 2 ampere. So on the galvanometer, I will rub that scale and instead of 1, 2, 3, 4 milliamperes, I will write it 1, 2, 3, 4 amperes. So indirectly, it is measuring the small current, but I know how much the actual current is. So basically it is called as calibrating the scale. That's all. You measure something else, but you know what it corresponds to. I hope that makes sense. Okay, moving on to voltmeter. Voltmeter, it's very simple. Instead of a parallel resistor, you connect a series resistor. So the resistance is very high. So you will see the current which is drawn in a voltmeter is going to be very small. So if you have a device, you want to measure the voltage across it, a very small current flows through the galvanometer because it's very sensitive anyways. So that measures the voltage difference. This total voltage is also the same voltage here, and V is current into the total resistance. Both the resistors are in series. So resistance will be RG plus RS. So I into total resistance gives me the total voltage. This is the formula you use for a voltmeter. Ideal voltmeter has very high resistance, draws very little current. Keep this in mind. Okay. Cool. Will there be any error? Yes, there is always an error in voltmeter and ammeter. There is always going to be. Yeah, because any device, no measuring instrument will have zero error. Okay. Fine, guys. Let's move on. Okay. I think we are going to go to questions now. So here are your questions coming up on the screen. Start with this. A solenoid has these many turns per unit length, carries this much current. The field is this much. You take another solenoid which has these many turns, carries this much current. What is the magnetic field at the center? Let's start doing it. Come on, guys. We are on to problems now. Yes, Ranveer, these are PYQs. The initial questions are all PYQs. I have not mentioned the year, I guess. But yes, these are PYQs. Formula for solenoid. Correct? Mu naught Ni. Now use logic, you will get the answer. Earlier the turns were 200, now it has 100. So N is made half. Earlier the current was I, now the current is I by 3. So current is made 1/3. Naturally, magnetic field will become how many times? Half into 1/3 is 1/6 times. So basically the new magnetic field will be old field, which is this much, divided by 6. So approximately 1 point something, very close to 1, but 10 to the power minus 2. Yeah, so that should be option A, I guess. Option A. Everything has 1.05, so it was just the power of, oh, why are you guys saying this? No, why will it be that? 10 to the power minus 2. 10 to the power minus 2. Option A, guys. Yogesh, it is A, not C. Happens. Made a mistake. 1/6. Moving on. These are PYQs, guys. Moving on. A horizontal overhead power line, height of 4 meters, carries this much current east to west. The magnetic field below is how much? Let's try to solve this question. Horizontal overhead power line at this much height carries current from east to west. This is east, this is west. East, west. I'll be facing north. So whatever is inside will be north. East, west, north. Behind, whatever is coming out is south. This is south. Now, if this is where the current is, at certain distance below on the ground, the field will be mu naught I by 2 pi r. Now, according to the current's direction, place your thumb, the fingers go inside and come down, from down towards you. So the magnetic field will be obviously towards you. So if it is towards you, it has to be south. So north will be out of the question. Out of the question, obviously. It can't be north. It's going to come towards you. Hold the current carrying wire. See how the fingers come towards you from below. Okay, fair enough. Now just substitute the values, guys. So mu naught by 2 pi is nothing but 2 into 10 to the power minus 7. Current. What's the current? Current is 100. So 10 to the power 2 divided by R. What is R? R is nothing but 4. So this will be nothing but 0.5 into 10 to the power minus 5. So, yep, is that right? 0.5 to 10 to the power minus 5. That's 5 into 10 to the power minus 6. Yeah, that's option C. Obviously. No, it's not B. It has to be C. Very good. Let's move to the next question. Yes, Shreyas. I'm going to provide you DPPs after the session. It's in the form of V-quiz. Right now also, when you see in the description box, there is a link by the name of V-quiz. Click on the link. It will open up a V-quiz. Those has some simple problems which you can practice, and more problems. Obviously, crash course is there. All chapters assignments are going to be provided in the crash course. So be a part of the crash course. That's why I keep telling you, and it's just for 2,700 bucks. Okay. Next question. There is a rectangular loop of so much length. Current is so much. If there is uniform field in the positive Z direction for these orientations, which loop would be in stable equilibrium? Let's try to understand this. Stable equilibrium. So when we talk about stable equilibrium, it means that if you have a loop which carries current, it has some magnetic moment, and you see that the magnetic moment is aligned, it's completely aligned with the field, then you will see that the torque is 0 and it is going to be in stable equilibrium condition. So all you need to see is where the magnetic moment is in each case. In this case, you turn your fingers like this, the magnetic moment comes along the X direction. No, wrong. In this case, the current is going like this. So magnetic moment will come this way, I think B should be the answer. But still, I'll just do a check. Current is going like this. So I think the magnetic moment will go this way. This is where the M will be. And the last one, the current is going like this. So I think the magnetic moment will be like this. So it is not parallel, it's anti-parallel. All the other three options are wrong. This will be correct. Done, done, done. Dr. Tech, if you are seeing the chapter right from basics, I have a feeling you should go see my Pathfinder playlist. Always. Like you are starting from literally nothing. This is a series meant for revision, or you have some idea about the chapter and now you want to scale up and then realize what are those topics which you need to focus on. That's when Zero to Superhero series will help you. Okay, that's how it builds on you. Moving on, next question. A uniform electric field and uniform magnetic field are acting along the same direction in a certain region. If an electron is projected along the direction of the fields with a certain velocity, then what will happen? IIT aspirant no Menti bacha. The Menti is in the form of V quiz now. So we no longer call it Menti, it's called as V quiz. The link is there in the description box. You can solve it as homework. That's what, it's like DPP, daily practice problems. Okay. One shows for him, why would sir take? Yes, obviously. Definitely Shreyas. Okay. Let's move on. A uniform electric field and uniform magnetic field are acting along the same direction in a certain region. Electric field, oops, what happened? Okay, electric field and magnetic field are in the same direction and you're throwing the particle also in the same direction. If an electron, it's an electron, negative charge. So if it's a negatively charged electron, obviously the force on it will be this way. Due to the electric field, force due to the magnetic field is obviously going to be 0 because V is parallel to B, so no force. So because of this force, what will happen? This velocity will decrease. Force is opposite. Hence, the answer is velocity decreases. Not option A, Yogesh. You are getting it wrong. Okay, no. How will velocity increase? It's an electron. So for electron, it will decrease. If it was a proton, then the answer will be increase. Is that okay, bacha? Okay, very good. Let's move on to the next one. Himanshu, Hall effect is basically where you see that current is passed through a conductor and you place that conductor in a magnetic field. You will see, because these are moving charges, the moving charges get deflected, they get accumulated on a certain side, and because of that there is a potential difference created in the conductor. So current carrying wire placed in a magnetic field, the charge carriers separate and you see a voltage difference created. That is called as a Hall effect, based on the concept of effect of magnetic field on moving charges. That's all. Okay, we have a deuteron. Deuteron is nothing but a proton and a neutron together. It's an isotope of hydrogen. This much energy is in a circular orbit of this much radius, perpendicular to the magnetic field. The kinetic energy of the proton that describes a similar orbit in the same plane with the same field is how much? Let's try to see this. Okay, now let's try to do this question very systematically. A lot of things are same, a lot of things are not same, and I think I might need some more formulas. Let's see, circular orbit, and that only happens when velocity is perpendicular to magnetic field. And I think I know the radius formula. I just told you it is mass into velocity by QB, and mass into velocity is momentum. So I'm just keeping it like this for now. Now kinetic energy is also mentioned. So I know one more formula, and that is kinetic energy is momentum square by 2m. Naturally, momentum will be root of 2 times m times k. That's momentum. Obviously, I'm going to substitute it here. So let's see, what do I get? So this will be root of 2 times mk divided by q times of b. Fair enough. Now I think I want to know the kinetic energy. So I'm just going to square this and see what happens. So r square is equal to 2mk by q square b square. So from this I will get the value of kinetic energy to be, all these people go over here, r square q square b square comes over here, divided by 2m. That's it. So this is the formula which I got right now. Okay, now there are two situations. First situation, this is the kinetic energy. Second situation, it's a different kinetic energy. The charges also are different because one's a proton, one's a deuteron. So let's divide it. Kinetic energy of a proton divided by kinetic energy of this deuteron will be, think carefully, radius ratio. Oh, the radius here and here is same. So in the ratio, it will just get cancelled out. Don't even worry. 2 is a constant, don't worry. Charge, well, it will be charge of the proton upon charge of the deuteron. I'll just keep it as it is, square it. Square is there. Field, same field. So don't even bother putting the field. Mass, oh, they are two different things. So mass will come, but inversely proportional. So mass of proton and mass of deuteron. Fair enough, guys? Okay. Now, moving on. I don't know, bacha, whether it's bit sat question or not. It doesn't matter. Just let's solve this, bacha. How does it matter? If I put bit sat, if I put COET, if I put mains, if I put NEET, the question, it will come anywhere. You don't know. And they're not going to see like, oh, this came in bit sat. I'm not going to put it here. Oh, I just change the values and put it. Who knows? Proton and deuteron, what is the charge? What is the charge? Yogesh, they are basically two particles put in the same field, and we know that whenever you put charged particles perpendicular, they go in a circular path. So I started with the radius formula and kinetic energy formula, but I don't want momentum, so I've substituted momentum here. And since the final question demanded kinetic energy, so I have rearranged this equation by squaring and rearranging it to find the kinetic energy. Now kinetic energy of both the particles, when you divide it, many similar things are there, like radius is same, 2 is same, field is same, so they will get cancelled. So it will be only the ratio of charge square by mass. Charge square by mass, charge square by mass, that's all. What now? It's the same thing. Charge is same, so plus E and plus E. There you go. Mass of deuteron and mass of proton? That I know. Deuteron is 1 proton, 1 neutron. Proton is 1 proton. So it is 2:1. Done. This is kinetic energy of proton. Deuteron's kinetic energy is 50. So kinetic energy of proton is 50 times 1 by 1 cancel into 2, which is 100. That's the answer. There you go. 100 kilo electron volt. That's it. Yes, Krishna, that's what we did, right? We took the ratio. I just give charge as benefit of the doubt because there are two different things. So yeah, maybe charge is different. Maybe one is alpha, one is beta particle. So I just put it like that. I know that both are same. So I can anyways cancel it out. I just wanted to explain that the charge is same. That's why I put charge. Otherwise, I would, if I had to solve it in the actual exam, I won't even do that. It's not complicated. Oh my God. No. These are the most common questions. IT aspirant. If you're an IT aspirant, you open up 2021 paper, there will be so many questions on just this concept. Charge particle thrown, kinetic energy is given, a radius ratio, a magnetic field ratio, or momentum ratio, angular momentum ratio. What is the other particle going to be? So many questions on just this. Yeah. Now, what about this question? There is this wire which is bent in this shape. Find the magnetic field at the center. So whenever you see these kind of shapes, always split it up into two parts. The first one is the straight wire. The second one is the curved wire. Let me tell you, when you have a straight wire which is carrying current, it always produces a magnetic field around it. Around it, the field is there. But on the axis, the field is 0. On that wire, there is 0 field. Around it, there is field. If you take this wire, O is on the axis, so there is no contribution of the wire, straight wire. There is no contribution of the straight wire. Now, the next thing is, what about the arc? What about the arc? Well, I know that for a complete loop, what is the magnetic field? It is mu naught I by 2r. That's the formula. But this arc is 3/4 of the complete circle. So you just multiply the fraction 3/4. That's it. Done. So 4 2s are 8. So 8 should be there in the denominator. 3 should be there on the top. So I think there is only one option like that, which is D. Done. Okay guys, that's it. Done. Multiply by 354. Very good, Ranveer. Okay, let's move on to the next one. Oh, beautiful question. There are 2 points, A and B, random points. There is a loop, there is a battery, current goes, spreads, comes back and comes back over here. Question is, what is the magnetic field at the center? This is also very common question in JEE Mains and other competitive exams, be it CETs and BITSAT. Very standard question. You should know it. Now, what happens in this situation is that the current which enters in, it splits into 2 parts. It splits into 2 parts. One part is this one, the big one. Let's say I call it I something. And this current over here also goes like this. Before again meeting at that point and coming back. Now, here is the concept. These currents, do you think they will be equal? If you thought they are equal, you are wrong. Reason, this path length and this path length are different. And we all know that the resistance is directly proportional to the length, and the current, current is inversely proportional to the resistance when it divides, when it splits. So current is also inversely proportional to the length. So more length will have less current, less length will have more current proportionately. Hence, I can clearly say that this current is higher. Oh, large length lower. My bad, sorry. This current will be lower because more length means less current, and this current will be higher because it has a smaller path. As simple as that. Fair enough? Now the next concept. Field due to each one of them. This will create a field inside, and because a lot of the loop is there, it will create more field. It will create more field inside. If you look at the other part, which is this one, current is this way, it will produce a field towards you. It will be slightly less, but it is compensated by the higher current. Look at this. Although the wire length is more, so it should create ideally more field, but do not forget the current here is less and the current here is more, so technically speaking they will compensate each other, and because of which they will cancel and the net field becomes 0. I hope this is clear. Okay, so the answer is 0. Got it, my warriors? Shreyas Paliwal, 20% is remaining. But remaining 80%, if it is pakka, then at least till June 10th, if you can do 90%, that will be good. And after your first attempt, maybe you can complete the remaining 10% if you want to, or else, I don't know, there is not too much time for 20% syllabus. You can at least do 90 to 95%. It's not needed that you complete 100%. Okay? So I would suggest ki in that 80% also, if you master all those 80% concepts, you can get even about 200 plus. It depends on what you have left. 20%, it should not be like electromagnetism, obviously then it will be difficult. If you have done all the major topics, you can easily get about 200 plus in the JEE Mains exam. Okay. Optics, viscosity, surface tension and waves. Oh my god. Viscosity, surface tension, it's okay. Optics and waves, please try to do it. Bacha. Optics is, fir bhi you can do it. It's not so difficult, at least for the mains perspective. Please try to do optics. Waves, try to do it from one shot. You will get a good understanding. And then if you, basically I'll tell you what, do standing waves and beats, Doppler effect and velocity. That's major thing in sound waves and all of that. Okay, let's talk about this one. There's a coil of this many turns, this much diameter, this much current. It's to be turned by some angle, this to this, in a magnetic field of this much Teslas. what is the change in the magnetic potential energy? Magnetic potential energy. Let's try to do this question. So change in the magnetic potential energy, that means delta U, that means final energy minus initial energy, that means energy when it was 180 degrees minus energy when it was 0 degrees. Is there a formula for a loop which is placed in a field which gives me the energy of the particle? Yes, there is. Torque was P cross E, energy was minus P dot E. Oh, let's use that. So minus P, oh, this is not P, sorry, M, because magnetic dipole moment, minus MB cos 180. That's the dot product. Minus 0 degrees, so it will be minus MB cos 0. That's it. Now, this will be minus cos 180 minus 1. So minus minus becomes plus MB. This minus becomes plus. Cos 0 is 1. So it will just be MB. So it will be 2 times of MB. That's it. Done, done, done. Now what is next? We have to find the change in energy. Oh, the values are given. So put it. So what is M? M is nothing but NIA. And this is B. So start substituting. Number of turns, 100. So put 100. Current, 1. Area, radius is given, I think, yeah. So pi into diameter is 20. So radius will be 10 centimeters, which is 0.1 meter. So just put 0.1 square, that's the area. Magnetic field is 5. That's it. Done, done, done. Solve it, you should get the answer. Just check it out. I think it should be either D or A. It should be either D or A. B and C are ruled out because 2 5s are 10. So pi is remaining. Pi means 3.14. So 3.14 into 10 to the power something. So it can't be C, it can't be B. That's how you can eliminate options even in real examination, by eliminating based on the numerical values and ignoring the powers of 10. So yes, it's 31.4 joules. Very good. It's not A. No, it's not A. Yeah. So there is a power of 10. Yeah. Moving on. Next question. We have a galvanometer, a resistance of this much gives full scale deflection of this much with this much current. That's the maximum limit of the current. How much resistance should be connected to convert it into an ammeter of 10 amperes range? Let's try to draw the diagram, especially for these questions. Don't try to do it mentally. You will always make some kind of a mistake. So you have a galvanometer. The maximum limit of the current, you should show it, 0.01 ampere. The resistance of the galvanometer is 100 ohms. Show that as well. And you also have to show a shunt resistance like this. RS value I do not know, but there will be some current IS, and this current is already shown. It's given that the range is 10 amperes. So that means 10 amperes enters inside, but only a part of it makes it here. So where will the remaining go? Obviously it will go here. So IS will be nothing but 10 minus 0.01. That's almost 10, guys. I mean, like, come on, 10 minus 0.01. That's like 9.99, which is like almost like 10. Okay, fair enough. Now what did I tell you? That these two resistors are in parallel. So hence RS by RG will be IG by IS. That's all. So RS I do not know. Galvanometer is 100. IG is this much. So 0.01 and IS is roughly 10. So just do the math. So RS is going to be 1 by 10, which is 0.1 ohm. That's it, done, done, done. It's very easy. You should just use resistance inversely proportional to current because they are in parallel. And remember the diagram, you get the answer. 0.1 ohms, yes it is. No, it's not B, be careful. Pariti, you have magnetism, atom and nuclei pending. Magnetism as in like the bar magnetism, Earth's magnetism, or the magnetic effects and sources, wala magnetism. Accordingly, I will tell you. Moving on, next question. Okay, this time I think we have a voltmeter question. Let's try to do this. Galvanometer has this much resistance, these many divisions. This much current gives 1 division deflection. So the question is, what is the series resistance to be connected? Okay, let's try to draw the diagram first. So galvanometer has a resistance of 50 ohms and series resistance, and you will connect it like this across some voltage. What's the voltage? Range of 25 volts. So So this is a 25 volt voltmeter. RS I do not know. That's it. Let's try to do this question, guys. Current is given per division. One division, this much current. 25 divisions, how much current? Because this is your full scale. So full scale deflection current, that means I max. 25 divisions are there. Per division there is 4 into 10 to the power minus 4 amperes. So 25 4 is 100. So this will be 10 to the power minus 2 amperes. That's the maximum current that can go. Now show that current which is going, that is 10 to the power minus 2 amperes. Now this 25 volts by Ohm's law will be the current into the sum of the resistances. That's it, IR. So the current is 10 to the power minus 2. RG is 50. RS I do not know. And this side is 25. So this will become 2500 is 50 plus RS. So therefore RS will be 2450 ohms. That's it. Where is the 2450? Oh, 2450 is there 2 times. Is this shunt or series? Oh, definitely not shunt. It has to be series. Shunt is ruled out. It's a voltmeter. For voltmeter, it is in series, not in shunt. Shunt is parallel. That's for ammeter. Parithi, if magnetism and matter is left, then please do atom and nuclei. That is having more or higher weightage. Okay, Parithi Mahesh, please complete atoms and nuclei and photoelectric effect, whatever is remaining, X-rays. That is very easy. I have my series. Use the crash course if you want. Solve the problems, practice in the crash course, solve the assignments of the crash course. You will be for sure salted in life. Moving on to the next question. Two magnets of exactly equal lengths have magnetic moments M1 and M2. What will be the effective magnetic moment if both these magnets are placed one over the other with similar poles? Similar poles. Hello, Hema Kumari. Let's try to do this. It's very easy. Similar poles. This is plus M1. This is minus M1. And another magnet over here, minus M2 plus M2. If you combine them together, it becomes one big magnet, same length. So here you will have M1 plus M2. That will be the new pole strength. And here it will be minus M1 plus M2. So basically it just adds, guys, that's all. It's just simple addition. You're placing north over north, south over south. That's it, as simple as that. So you will see it will be M1 plus M2, as simple as that. Oh no, why by 2? Nope, not by 2. It's just simple addition. Thank you, Hema Kumari. Means a lot. Thank you for all the love, guys. And I hope you have showered your love by, smashing the like button. It means a lot. Like, why does sir keep asking why smash the like button? Because that's how we reach more students. Okay? Only when you like, when you subscribe, you watch, and you comment, that's when, all other students in the country will be able to, access and get to know about the channel. Otherwise, probably it will not show up in the recommendations. Okay, moving on to the next one. A magnetic needle suspended by a silk thread is vibrating in the Earth's field. If the temperature of the needle is increased by a significant amount, then what will happen? Think about it. If it is increased by significant amount, then what will happen to that magnetic needle? First of all, think, why will it be vibrating? It is vibrating because when you take a magnetic needle north-south and you place it in somebody else's field, deflect it, you will see there will be a torque. This torque is restoring in nature, hence it will perform oscillations, hence it is vibrating. That's what it is. Now what happens the moment you have increased the temperature by a significant amount? You basically have destroyed the magnetic properties. Beyond a certain limit, the magnet will no longer remain magnetic. It will basically get completely destroyed. All the alignments will be gone. That's it. It will get demagnetized. So once it is demagnetized, no torque, no restoration, no oscillation. That's it. So basically, the magnetic needle stops vibrating. That's the answer, Darshini. No, it does not increase. Okay, a lot of people feel that it should increase or decrease some logic. No, the magnet itself gets destroyed, as simple as that. Okay, so that's a simple one, but quite tricky also. A compass needle. Yeah, Yogesh, you will definitely understand magnetic properties and effects. There's a lecture, Pathfinder series, watch it. As simple as that. Oh, V-Quiz links needs my permission? Oh, I need to check on that. PL, thank you for pointing it out. I'll have a look at it. A compass needle which is allowed to move in a horizontal plane is taken to a geomagnetic pole. What do you think will that compass needle will do? So we have a compass needle, let's say like this, and we are taking it to a pole. So this is your pole, and we know at a pole what happens is that the field lines are vertical. The field is always vertical, maybe in or up, doesn't matter, but it's always vertical. Now why did I show this is because I know this magnetic needle has a magnetic moment like this. Field is like this. If you do M cross B, you will notice that M cross B will definitely create a torque like this. Now this torque is coming towards you, or basically in the horizontal plane. So the needle would tend to bend like this in a vertical plane. Understood? But it is allowed to move in a horizontal plane. It wants to bend like this, but it can only move in horizontal. What will happen? It can't move. That's it, it will be stuck over there. But now you will be confused. Will there be no movement or east-west? No, north-south. It will stay in any position because over there is nothing like north, east, west, south. Whichever direction you keep it, it stays there. So C and D is getting eliminated. Will it stay in this or this? Rigid? No, it can't be rigid because if you move it, it will stay there. If you move it, it stays there. So it's not rigid. Rigid means you move it, it does not budge. It tries to stay there. That's rigid. So it's definitely not rigid. It will stay in any position that you leave it to. That's why it is option B. Tricky. Very similar options, but you need to have good visualization. You have to simulate it in your head. Rigid. Oh, no. It can stay anywhere that it likes. Doesn't matter. Wow, we are done. So remember, V-Quiz link is there in the description box below. Please check it out. That's your regular DPP for free on the channel. Apart from the assignments that you will get in the crash course. The crash course will give you lots of material which will keep you busy till the second attempt for sure. And you will have 120 classes. This crash course is going to be a life-changing decision in your career. Let me tell you that. And even if you are enrolled in any other crash course or any other course or a part of already some coaching institute, this crash course will give you a different perspective, a different set of questions for solving. Not just that, mock tests as well. This is for NEET as well as JEE. For JEE also you have the same thing with exams, with mock tests, and the validity is till your last date, not 3rd July, till whatever is the last date of the exam. You will get notes, assignments, mock tests, class doubt solving, everything. It's just for 2,700 bucks. Link is there in the description box below. I can just show it to you right now over here. So let me just open it. So right now while you're watching this lecture, see over here, JEE crash course, NEET crash course. If you click on this link, you will see this is a batch. Now there is only one batch. Don't expect a new batch because the course itself is for 5 weeks. And if you start now, you can complete the recordings, most of it by the first attempt, and few of them, if you are very confident, you can leave that. And if you feel like, you can watch it after the first attempt. Now you can see all the things. How will this course help you? What are the batches teach us? I'm in fact going to be teaching in the crash course, results, testimonials, study materials, what kind of learning, test series, and what kind of strategy sessions you will get. Everything has been mentioned right now over here. This batch is in pure English. There's also a Hindi English batch, but I'm pretty sure you will be interested in English. And you can just click on this. You will save a lot of money right now. You can see you have saved 12,300 bucks. You get it only for 2,700. Use any of the options that you would like. And if you want to join the NEET course, this is a link you will click on. Same price, same deal, same mock tests, but obviously NEET pattern, NEET assignments and all of that. again in English medium. So that's about the crash course which you should use apart from your regular Zero to Superhero series. All right, I cannot find my gravitation lesson. Well, the gravitation lesson is going to be right here, bacha. I mean, just go to YouTube, just go to playlist. Okay, just go to playlist. Fine, go down, go down, go down. See, class 11th. Yes, just click on this and you will see waves. Oh, where is gravitation, man? Oh, now even I'm not able to find. Is it? Okay, just one second. It's there somewhere. I don't know, it is there somewhere. Okay, let's just see and open this playlist. This is the complete playlist. Maybe it is there somewhere here. Oh, there I think I saw. Yeah, gravitation. See, gravitation lesson 1, lesson 2, lesson 3. All these classes are there. It's right over here. Okay, there you go. Acha, it's saying please wait for the teacher to start the quiz. Let me just try this. See if it works now. Go to the joining screen. Start the first question, next 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 question. Oh my god, I think I'll have to conduct this week quiz. Oh my god, I have to play this week quiz. Okay, I'll have to play it myself and press next 100 times. Okay, fine, I'll do that. That's one jobless thing I need to do. All right. Good night, Jamesburg. Good night, Pagal. Have a great time. Okay. Bye, Sonalika. Thank you so much. Sriji came in late, I guess. Okay. I didn't take, but computer science I've been watching for one shot. Should I change my choice to videos to JEE series? One for JEE, one for NEET. I don't take bio, but take computer science. Devraj, you should obviously watch JEE series, obviously. Oh, now only JEE crash course over. No problem. Okay. Bye-bye, Nadeesh. Bye-bye, Vishli. Bye-bye. Take care, Hemant. Have a great time. See you guys again tomorrow for EMI and AC at 7 o'clock. Saturday, do not forget motivational sessions and casual talk session. All for you. Have a great time. Hasta la vista. This was Captain Shreyas.